All right, so what have we done so far? We've only shown that Dijkstra's works for a single example. That's not enough to prove correctness. You can use a proof for contradiction. For example, it's good for demonstrations and it's good for contradictions, but you can't use a proof, a single example to prove the correctness of an algorithm. So instead, what we're going to do for Dijkstra's is a proof by induction. So let me remind you of how a proof by induction works. We want to prove some property, for example, that Dijkstra's works on graphs with n vertices. And by works, I mean it finds the shortest path from the start vertex to all other n-1 vertices. And you start that usually by talking about the base case. So our algorithm holds because, something about the code or the problem. So if we have a graph with a single vertex, it's easy to compute the path from the start vertex to itself, and there's no other vertices that we care about. Next, we assume some property that holds when we work on some subset of the problem. So instead of taking a look at all n vertices, we're going to look at k vertices, where k is just some number less than n. And that we're going to call that the inductive hypothesis. And then we make some comment about how p of n holds because, well, we assumed p of k holds and then make some sort of reasoning about what the code actually does when to add a vertex to the set of found, for example. Then we can just say, thus by induction, p of n holds for all n. And that process works because we have the base case, and we also have this property where we go from k to n, and we basically can just apply that here, and here, and here, and here, and we can track that process all the way up to n, because it's the same step along the way. So that's our general process for a proof by induction. So here's our theorem for Dijkstra's. For every graph with non-negative edge links, Dijkstra's algorithm computes all shortest path distances from the start vertex to every other vertex. And again, that is under the assumptions that the graph is connected, meaning that such a path exists, and that there are no negative edges. Our base case, we sort of just do simply in code here. We're just going to say the length of the path to the start vertex is equal to 0. And that's really all we have to say about the base case. If that's the only vertex in there, we're done, and it holds. The theorem above holds. Now our inductive hypothesis is essentially a restating of this. We're going to assume that all previous iterations produce correct shortest paths, and that for all v found in found, so all the vertices that we've already been found, the length of the v, lengths of v is equal to the shortest path length from the start vertex to v. So those are just essentially two ways to say the same thing. So we're assuming that our algorithm is correct for k vertices, where k is any sort of intermediate iteration of Dijkstra's algorithm. All right, our next step here is going to be to look at the inductive step. So we've stated our inductive hypothesis. How about the inductive step? So for the inductive step, we basically have to look at what our code is actually doing. And what our code is actually doing is it's extending our found set. It's these two lines here that really matter. It's extending our set of found vertices by 1 and setting the path length to a single vertex. So what do we do in each iteration? Let me state this a little bit differently than what it is in pseudocode. And in the current iteration, we pick an edge, and we'll call it v star v min. So v star is just the vertex that we already know the path length to. We're already assuming that we have the minimum path length to that, and we're going to use our inductive hypothesis for that. And v min is the one that has the smallest value according to Dijkstra's greedy criterion. We add v min to our found set, and we set the path length of v min equal to the length of the path to get to v star, which we've already computed, plus the weight going from v star to v min. So what do we already know about the length here? So the one that shows up here. What we already know about that is that due to our inductive hypothesis, we know that that has to be the minimal path length. All right, there's just one last piece to this proof, which is that we already have the optimal path to v star, and we will not find a better path to v min. There's no possibility that later on we'll have found a better path to v min than what we just computed. So how do we prove this? There's a number of different ways you can go about it. I think the most straightforward process is to do this by a loop invariant. So let's assume that we've done that by loop invariant. We're actually going to do this a little bit more simply. You can look at a loop invariant. You can find a number of resources for that. I think I'd rather you get an intuition for this, so we're going to look at this in terms of some actual graphs and just sort of eliminate that there's another possible path to vmin, and we'll do this a little bit differently than a loop invariant. But assuming that there's no better path to vmin, what we can say is that by our inductive hypothesis, Dijkstra's algorithm is correct. So we've got the base case, we've got our inductive hypothesis, we've looked at a single iteration and said that assuming this loop invariant holds, that we've got a shortest path to vmin. And then our last thing here to do is just to tie up our reasoning by saying, thus by induction, P of n holds for all graphs. All right, well, let's focus on this in the next video. How do we know that there's no shorter path to vmin?